A warm welcome to you. I'm really glad you're here today. Before we begin, I'd love for you to pop into the comments and let us know where you're listening from and what the local time is for you. It's always beautiful to see how global this little space has become. A big thank you to those who have subscribed and supported by liking videos. It truly helps this channel flourish. And if you'd like me to cover something in the future, your suggestions are always welcome. So now, let's begin. Chapter 1: Birth of a Star, From Nebula to Formation. In the vast expanse of the universe, where darkness stretches into infinity, lies the birthplace of stars, a nebula. A nebula is a stellar nursery, a magnificent cloud of gas and dust, shimmering and swirling with potential. These celestial clouds are primarily composed of hydrogen, the simplest and most abundant element in the universe, along with helium and a smattering of heavier elements. Imagine a vast cosmic canvas, painted with vibrant hues that shift and change as light dances through the particles. Nebulae can vary in size and type. Some are bright and colorful, illuminated by the light of young stars, while others are dark and foreboding, obscuring the light from objects behind them. The Orion Nebula, for example, is a stellar beacon that captivates the eye with its radiant colors, showcasing the beauty of star formation. On the other hand, dark nebulae, such as the Horsehead Nebula, appear as voids against the backdrop of the cosmos, hinting at the mysteries hidden within their depths. As we gaze upon these magnificent formations, we encounter the magical process of gravitational collapse. Within the cold embrace of a nebula, regions of higher density begin to emerge. These areas start to draw in surrounding gas and dust through the force of gravity, creating a swirling mass that begins to fragment. Picture a gentle whirlpool where the water converges and spins, pulling inward with an irresistible force. This is the beginning of a star's journey. As the cloud fragments, the individual clumps grow denser, and their gravitational pull strengthens. With each passing moment, they attract more material from the nebula, increasing their mass. This process is akin to rolling a snowball down a hill, where it gathers more snow as it rolls, growing larger and larger. It is a delicate balance, where the inward pull of gravity competes with the outward pressure of heat generated from the collapsing material. As the fragments continue to collapse, they form what we call protostars. These protostars are the early stages of star development, nestled within the cocoon of gas and dust that surrounds them. Imagine a warm, glowing ember hidden in a pile of ash, waiting for the right moment to ignite. The temperatures inside these protostars rise dramatically as they accumulate mass, reaching thousands of degrees. It is in this phase that the forces of nature begin to work their magic. The transition from protostar to star is marked by a process called accretion. As the protostar gathers material, it creates a spinning disk of gas and dust around it, known as an accretion disk. This disk is a bustling hub of activity, with particles colliding and merging, slowly building up the mass of the nascent star. As matter spirals inward, it releases energy in the form of heat and light, illuminating the surroundings. As Carl Sagan once said, "The cosmos is within us. We are made of star stuff." This profound notion reflects the intricate connection we share with the universe. The materials that form our bodies were once part of distant stars, born from the same processes that shape the cosmos. The journey of a protostar is not a solitary one. As it evolves, it may find itself surrounded by other protostars, creating clusters that share the same nebula. These stellar siblings interact, their gravitational forces influencing one another as they grow. Imagine a gathering of friends, each with their own unique story, yet bound together by a shared experience. Over time, as the protostar continues to accumulate mass and the core temperature rises, nuclear fusion ignites. This moment is nothing short of a cosmic miracle, where hydrogen atoms begin to fuse into helium, releasing an immense amount of energy. This energy creates an outward pressure that counteracts the pull of gravity, leading to a delicate equilibrium that defines a star. As the fusion process takes hold, the protostar transforms into a main sequence star, a vibrant beacon of light in the celestial landscape. This is a crucial stage in a star's life, where it will spend most of its existence, shining brightly for billions of years. To imagine the birth of a star is to envision the profound interconnectedness of all things. Each nebula, each fragment, and each protostar is a testament to the ever-evolving nature of the universe. This cosmic dance, filled with chaos and beauty, reminds us of the cycles of creation and destruction that govern the cosmos. As we reflect on this extraordinary process, we are left to ponder the mysteries of the universe. What stories do these stars have to tell? What unseen forces shape their destinies? In the quiet moments of contemplation, we may find ourselves connected to the very essence of existence, floating amidst the stardust that binds us all. The birth of a star is but the beginning of its journey. From the swirling depths of a nebula to the radiant light of a main sequence star, every step is a marvel of cosmic engineering. And as each star takes its place in the night sky, we are reminded that we, too, are part of this grand narrative, woven into the fabric of the universe. As the protostar radiates its initial light, the surrounding nebula begins to undergo a transformation. The energy released from the burgeoning star initiates a complex interplay of forces within the cloud itself. Imagine the gentle caress of warmth spreading through the cold gas and dust, igniting reactions that will shape the future of the nebula. This energy not only illuminates the area, but also influences the dynamics of the surrounding material. The intense heat from the protostar causes nearby gas to begin to evaporate and dissipate, creating a vast expanse that will one day become the interstellar medium. As this material is pushed away, it creates a cavity around the newly formed star, marking its presence in the cosmos. Within this dynamic environment, interactions between neighboring protostars can lead to intriguing outcomes. Stellar winds, the streams of charged particles emitted by young stars, can collide with the remnants of the nebula, compressing the gas and dust even further. This compression can trigger additional rounds of star formation in regions previously untouched, perpetuating the cycle of creation. One might wonder, could this be the birth of future companions for our young star? The birth of stars often occurs within clusters, where gravitational forces bind them together in a cosmic embrace. These clusters can range from a handful of stars to thousands, sharing the same origin and fate. In such environments, the mutual gravitational attraction plays a crucial role in their evolution. Stars born in clusters often exhibit similar ages and compositions, as they form from the same primordial material. Among these clusters, some stars may evolve more rapidly than others, leading to a fascinating spectrum of stellar life cycles. While some will become massive giants, radiating their energy with great intensity, others will remain smaller and cooler, quietly illuminating the cosmos. This beautiful diversity serves as a reminder of the myriad pathways that exist within the cosmos. As we delve deeper into the life of a protostar, we encounter the concept of accretion in greater detail. The accretion process is not merely a passive gathering of material. It is a dynamic and intricate ballet of physics. As dust and gas spiral toward the protostar, they form a rotating accretion disk. Picture this disk as a vibrant whirlpool, with particles swirling and colliding, each interaction creating heat and energy. This energy is pivotal, as it raises the temperature of the protostar's core. Eventually, it is this heat that fuels the ignition of nuclear fusion, the transformative process that defines a star. The moment fusion begins is profound. It is akin to the spark that ignites a long-awaited flame. The star enters a state of equilibrium, balancing the inward gravitational pull with the outward pressure from fusion reactions. But the journey of a star does not end with its ignition. As it enters the main sequence phase, the star will embark on a journey that lasts for billions of years. This stage, characterized by the fusion of hydrogen into helium, is marked by stability and brilliance. Imagine a lighthouse standing resolute against the storm, guiding ships safely to shore. In a similar fashion, main sequence stars serve as beacons of light, illuminating the darkness of the universe. The life of a star is not without its challenges. Throughout its existence, it will face trials that shape its destiny. As it exhausts its hydrogen supply, the star will undergo dramatic changes. The core contracts, and the outer layers expand, leading to the formation of a red giant. This evolution can lead to spectacular events, such as supernovae, where a dying star releases an explosion of energy so powerful that it can outshine entire galaxies for a brief period. In contemplating such transformations, one cannot help but reflect on the words of physicist Richard Feynman, who said, "The imagination of nature is far greater than the imagination of man." This sentiment resonates deeply as we observe the incredible processes taking place within the universe. Each star, in its life and death, tells a story far beyond the limitations of our understanding. As we witness the birth and evolution of stars, we are reminded of our own place within this grand cosmic narrative. The very atoms that compose our beings were once forged in the hearts of stars, echoing the interconnectedness of all life. Each moment we gaze at the night sky, we see not just distant points of light, but a rich tapestry of histories unfolding across the vastness of space. The birth of a star, from the stillness of a nebula to the vibrant light of a main sequence star, is a testament to the beauty of cosmic processes. It invites us to ponder the wonders of existence and the forces that shape our universe. What other mysteries lie hidden among the stars? What stories do they hold, waiting for us to discover? In the quietude of the cosmos, as stars form, evolve, and eventually fade, we are offered a glimpse into the cycles of life and death that govern all things. The birth of a star is not just a phenomenon. It is a reminder of the beauty that emerges from chaos, a dance of creation that continues to inspire and captivate our imagination. As we embrace this understanding, we find ourselves not merely as observers, but as participants in the unfolding story of the universe. As the cosmic clock continues to tick, the protostar's evolution unfolds further, leading us into the intriguing realm of accretion and the forces that shape it. The accretion disk, a swirling mass of gas and dust, serves as the crucible of creation. Within this vibrant disk, particles collide and merge, generating heat and energy that further fuels the protostar's growth. Imagine a bustling marketplace where vendors trade their wares, each interaction adding to the richness of the experience. In a similar way, the particles within the disk contribute to the burgeoning mass of the nascent star. As the protostar gathers momentum, the dynamics of its environment become increasingly complex. The gravitational pull of neighboring stars and the remnants of the nebula exert their influence, creating a symphony of interactions. Some protostars may find themselves in a gravitational tug-of-war, their fates intertwined with those of their stellar neighbors. Could these interactions lead to the birth of binary systems, where two stars share a common destiny? The energy radiating from the protostar also impacts the surrounding nebula, triggering a cascade of events. As it sheds heat, the protostar's intense light begins to sculpt the clouds of gas and dust, creating structures that reveal the hidden beauty of the cosmos. Picture the gentle caress of a warm breeze that shapes the landscape, carving valleys and hills. The energy from the protostar acts similarly, pushing and pulling at the material around it, sculpting the nebula into intricate forms. As the accretion process continues, the protostar experiences fluctuations in temperature and luminosity. This variability is a natural part of its development, a dance of energy that reflects the intricate balance of forces at play. At times, the protostar may flicker, momentarily dimming before bursting forth with renewed brilliance. Such changes are not mere fluctuations. They signify the dynamic nature of star formation, where stability and chaos coexist in a delicate equilibrium. As the core temperature rises, reaching critical levels, the moment of ignition approaches. The fusion of hydrogen into helium transforms the protostar into a fully fledged star. This transition is akin to the awakening of a dormant seed, breaking through the soil to embrace the warmth of the sun. The newfound energy generated by nuclear fusion creates a powerful outward pressure, counterbalancing the gravitational pull that seeks to compress the star into oblivion. With the onset of fusion, the star enters the main sequence phase, a period of relative stability and longevity. It is during this time that the star shines brightly, illuminating the surrounding cosmos and providing energy to any planets that may form in its vicinity. The balance of forces within the star allows it to maintain its luminosity over billions of years, a testament to the intricate workings of nature. In this vast expanse of time, stars may evolve differently based on their initial mass. While some may follow a predictable path, others may take unexpected turns, leading to fascinating outcomes. The life cycles of massive stars, for example, culminate in spectacular supernovae, while smaller stars like our Sun will eventually shed their outer layers, leaving behind a beautiful planetary nebula. Consider the words of astronomer Vera Rubin, who once said, "We are all made of stardust." This profound truth speaks to the shared legacy of all living beings in the universe. The atoms that form our bodies were forged in the hearts of stars, a seamless connection that binds us to the cosmos. Each star, in its own journey, contributes to the grand narrative of the universe, enriching the cosmic tapestry with elements that will eventually become part of new worlds. As we observe the birth and evolution of stars, we are invited to reflect on the cycles of creation and destruction that govern our existence. Each flicker of light in the night sky tells a story, a tale of transformation, resilience, and connection. What secrets lie within the hearts of these stars? How do their journeys mirror our own paths through life? In contemplating these questions, we find ourselves drawn closer to the very essence of what it means to be part of the universe. In this grand cosmic theater, the birth of a star is not merely an event. It is a reminder of the beauty inherent in the process of becoming. Each nebula, each protostar, and each stellar cluster embodies the delicate interplay of forces that shape our reality. As we continue to explore the universe, we uncover not just the mysteries of the stars, but also the profound connections that unite us all. The journey of a star, from the quietude of a nebula to the vibrant illumination of its main sequence phase, invites us to marvel at the intricacies of nature. It is a tale that resonates within us, whispering of the wonders that lie beyond the horizon. As we take this journey together, we are left with a sense of awe and curiosity, wondering what other mysteries await us among the stars. Chapter 2: Ignition of Nuclear Fusion, the Star Awakens. Within the heart of a forming star, a profound transformation is about to unfold. As the gravitational forces coalesce gas and dust into a dense core, the conditions necessary for nuclear fusion begin to take shape. The journey toward ignition is not a mere flick of a switch. It is a delicate balance of temperature and pressure, a threshold that must be crossed for the star to awaken. Picture the protostar, a swirling mass of gas, still cocooned in its dusty shroud. As it contracts under the weight of its own gravity, the particles within are drawn ever closer together. The friction created by this relentless pressure heats the core, raising the temperature to staggering levels. At this stage, the protostar is still in a precarious state, a mere whisper away from its potential. What does it take to ignite the fusion process? The answer lies in the incredible forces at play, the very forces that govern the universe itself. Hydrogen fusion stands as the primary energy source for stars, igniting a brilliant light that will shine across eons. It begins with the simplest of elements, hydrogen atoms. In the core of the protostar, these atoms, moving at unimaginable speeds, collide with one another. As temperature and pressure climb, the collisions grow more frequent and intense. The hydrogen nuclei, positively charged and naturally repellent, must overcome this electrostatic barrier to fuse. The energy released during this fusion reaction is astonishing, producing helium as a byproduct and releasing vast amounts of energy in the form of light and heat. Imagine a furnace at the heart of a star, its flames fueled by the very fabric of the cosmos. Fusion only occurs under conditions of extreme pressure and temperature, which can exceed millions of degrees. Within the core, temperatures soar to levels that defy comprehension, creating a dynamic environment where the laws of physics bend and dance in harmony. As the protostar's core reaches approximately 15 million degrees, the moment of ignition draws near. What happens as the core continues to heat up? The once chaotic motions of individual particles begin to find their rhythm. The immense pressure from the stellar mass above forces the core into a state where hydrogen nuclei can overcome their mutual repulsion. As the fusion process begins, the energy generated counteracts the gravitational collapse, creating a delicate equilibrium. This balance between the inward pull of gravity and the outward push of radiation defines a star's life. As the protostar evolves, it transitions into the main sequence phase, a stage that marks the beginning of its true life as a star. This transition is akin to a butterfly emerging from its chrysalis, a metamorphosis fueled by the ignition of nuclear fusion. In this phase, the star enters a stable state where it will spend the majority of its life. Imagine the brilliance of a sun rising over a tranquil landscape, casting light upon the world. Similarly, the ignition of nuclear fusion bathes the universe in radiant energy, illuminating the darkness of space. The newly formed star now shines brightly, a beacon of light and heat that will nourish the planets and other celestial bodies that form in its vicinity. As the star settles into its main sequence state, it becomes a master of balance, a celestial performer in a grand cosmic ballet. Throughout this stage, it will fuse hydrogen into helium at an astonishing rate, converting mass into energy according to Einstein's famous equation. Each fusion reaction releases energy, which flows outward, creating the light and warmth that we associate with stars. Throughout history, many great minds have pondered the nature of stars and their lifeblood, fusion. The insightful words of physicist Carl Sagan resonate deeply. The cosmos is all that is or ever was or ever will be. As we contemplate these celestial bodies, we can appreciate the complexity of their existence, where simple elements engage in a dance of creation, giving rise to the very fabric of life itself. With each pulse of energy radiating from its core, the star continues its journey through time, a steadfast guardian of the cosmos. The fusion process will sustain the star for billions of years, a remarkable feat of nature. As it ages, the star will eventually exhaust its hydrogen fuel, but for now, it thrives in the delicate balance of pressure and temperature, a harmonious symphony that echoes through the vastness of space. In this way, the ignition of nuclear fusion not only marks a significant milestone in the life of a star, but also serves as a reminder of the interconnectedness of all things. Every atom in our bodies, every breath we take, is tied to the stellar processes that occur in the universe. We are intimately connected to these celestial phenomena, existing as part of a grand narrative that stretches across time and space. As we explore the cosmos, let us marvel at the stars that dot the sky. Each one is a testament to the beauty and complexity of nuclear fusion and the remarkable journey from protostar to main sequence star. The universe is alive with stories waiting to be told, each star a chapter in the magnificent saga of creation. Through this lens, we can appreciate the staggering forces that govern our universe, the same forces that birthed the stars and continue to shape the galaxies. The ignition of nuclear fusion is not merely a scientific event, it is a cosmic awakening. With every star that ignites, a new chapter in the story of the universe begins, a tale woven into the very essence of existence itself. As the star's core stabilizes and hydrogen fusion takes hold, the surrounding layers of gas and dust begin to dissipate. The once dominant shroud of material that enveloped the protostar fades away, revealing the radiant brilliance of a fully formed star. This moment is not merely a transition, but a celebration of energy and light, a symphony playing across the universe. The forces at work within the star are complex yet beautiful. With every fusion reaction, hydrogen nuclei collide, forming helium and releasing energy that propels outward. This energy is not just a byproduct. It is the very heartbeat of the star, generating radiation that travels through layers of gas before finally escaping into space. Imagine this process as a gentle wave lapping against the shore, each crest representing a pulse of energy that brings warmth and light to the cosmos. Yet, what are the consequences of this energy? As fusion continues, the star enters a phase of equilibrium, where the energy generated from fusion matches the gravitational forces trying to collapse it. This delicate balance allows the star to shine steadily for millions to billions of years. Can we fathom the magnitude of such a timescale? A single star's life can span epochs, witnessing the birth and demise of countless celestial entities. The main sequence phase is characterized by this remarkable stability. Stars like our Sun reside here, harnessing the power of hydrogen fusion. They are the architects of their own longevity, becoming the nuclei around which planets form. As these stars shine, they produce a spectrum of light that can be observed across immense distances, illuminating not just their own worlds, but also the vast reaches of space. Consider the implications of this light. When we gaze at the night sky, we are witnessing the past, the echoes of stars that may no longer exist. Each twinkle is a reminder of the dynamic processes of fusion and energy release that have etched their stories into the fabric of the universe. The light we see has traveled for years, carrying with it the essence of stars and their life cycles. Among the stars, there are those that have captivated the minds of astronomers and dreamers alike. Take, for example, the iconic Betelgeuse, a red supergiant that lies in the constellation Orion. As it nears the end of its main sequence life, its surface temperature and luminosity shift, offering a glimpse into the varied evolutionary paths of stars. "We are made of star stuff," said Carl Sagan, reflecting on our connection to these celestial giants. With every glance at the night sky, we are reminded of our own origins and the cycles that govern life. The processes at play are governed by fundamental principles of physics, where temperature and pressure dictate the fate of stars. In the core, temperatures soar high enough to enable hydrogen nuclei to overcome their electrostatic repulsion. As fusion ignites, the resulting energy creates pressure that counteracts the gravitational collapse. This process is not merely a physical phenomenon, it is an illustration of balance, a dance of forces that sustain life among the stars. As the star exists in this stable state, It continues to fuse hydrogen into helium for eons, a quiet yet powerful act of creation. With each passing moment, the core transforms, as helium accumulates and pushes the star toward new evolutionary stages. The journey is not static. Rather, it is a testament to the dynamic nature of stellar life. Imagine, if you will, the vastness of a star's interior, where reactions occur at an immense scale. In a single second, billions of hydrogen nuclei fuse, creating energies that ripple throughout the star. The sheer volume of these reactions is mind-boggling, a reminder of the intricate processes that govern our universe. Each fusion event releases energy equivalent to an explosion. Yet in the heart of the star, this energy is harnessed, creating a stable radiative zone that gradually transports energy outward. As the star approaches the end of its hydrogen-burning phase, it transitions into a new chapter, one filled with challenges and transformations. While the main sequence is defined by the fusion of hydrogen, the exhaustion of this element compels the star to adapt. The core contracts, temperatures rise, and the star prepares for its next act. This transition is akin to a river carving its way through the landscape, shaping the environment around it. The star begins to fuse heavier elements, such as helium, carbon, and beyond, altering its structure and life cycle. It is a process that leads to a spectacular finale, where the star may eventually explode in a supernova, scattering its enriched contents across the cosmos and seeding new generations of stars and planets. What does this say about the cyclic nature of existence? The death of one star can give rise to the birth of many others, a perpetual cycle of creation and transformation. Each stellar life is a thread woven into the grand tapestry of the universe, contributing to the continuous evolution of matter and energy. In this way, the ignition of nuclear fusion is not just a moment of birth for a star, but a profound milestone in the universe's ongoing narrative. It is a reminder that everything is interconnected, that each star is a part of a larger story that encompasses creation, destruction, and rebirth. As we ponder the nature of these celestial bodies, we find ourselves drawn into the cosmic dance, reflecting on our place among the stars and the energy that binds us to them. In the vastness of space, the ignition of nuclear fusion marks the beginning of a star's life, a life that shines brightly, nurturing the worlds that form in its embrace. And as we continue to explore the cosmos, we carry with us the knowledge that we are part of this magnificent journey, a journey that invites us to not just look up at the stars, but to understand the profound processes that govern their existence and our own. Chapter 3: Main Sequence Phase: The Stable Life of a Star. As we journey beyond the ignition of nuclear fusion, we find ourselves in a remarkable phase of a star's life, the main sequence. This is the stage where a star truly comes into its own, radiating energy and light with a stability that can last for billions of years. Imagine a vast celestial orchestra, where each star plays its part in the grand symphony of the universe, resonating with a balance that has been expertly crafted over time. Main sequence stars are defined primarily by the fusion of hydrogen into helium within their cores. This process occurs under immense pressure and temperature, creating a balance between the outward push of fusion energy and the inward pull of gravity. It is this delicate equilibrium that characterizes a star's life during the main sequence phase. The energy produced by nuclear fusion generates radiation pressure, which counteracts the gravitational force trying to collapse the star inward. This state of balance is not just a transient moment. It can persist for eons, allowing these stars to shine brightly and steadily. Consider the sheer magnitude of this energy production. In 1 second, the Sun converts approximately 400 million tons of hydrogen into helium. This extraordinary process emits an immense amount of energy, equivalent to the energy released by the detonation of several hundred nuclear bombs. Yet, the Sun, a quintessential main sequence star, has been performing this feat for over 4 billion years. What does it take for a star to maintain such a relentless pace? The answer lies in a finely tuned set of conditions, where temperature, pressure, and composition come together in a cosmic dance of stability. As we reflect on the lifespan of a star, we realize it is not uniform. It varies dramatically based on the star's mass. More massive stars burn through their hydrogen fuel at an astonishing rate, living fast and dying young. Their lifespans may stretch to just a few million years. In contrast, smaller stars, like red dwarfs, exhibit a more leisurely existence, sometimes enduring for tens of billions of years. This discrepancy raises a fascinating question. Why do some stars consume their resources so quickly while others linger in the cosmic playground? The answer lies in the rate of nuclear fusion. More massive stars generate greater pressure and temperature, accelerating the fusion process. This rapid consumption leads to a short-lived, albeit brilliant, existence. To visualize this concept, imagine a campfire. A small, steady flame can burn slowly and persistently for hours, while a large bonfire, fueled by an abundance of wood, roars with intensity but burns out much faster. This analogy illustrates the relationship between mass and stellar lifespan. The larger the stellar mass, the more intense the fusion reactions, and consequently, the shorter the star's life. As we delve deeper into the characteristics of main sequence stars, we encounter the concept of stellar classification. Stars are classified according to their spectral characteristics, which reflect their temperature, luminosity, and size. The Hertzsprung-Russell diagram serves as a fundamental tool in this classification, plotting stars according to their luminosity and temperature. At the top of this diagram, we find the luminous, hot stars. At the bottom, the cooler, dimmer ones. The main sequence forms a diagonal band that stretches from the upper left, where the massive, blue stars reside, to the lower right, where the smaller, red stars can be found. This diagram serves not only as a classification system, but also as a window into the life cycle of stars. The position of a star on this diagram is indicative of its current state and future evolution. For instance, when we observe a star like Sirius, one of the brightest stars in our night sky, we learn that it is a main sequence star, significantly more massive and hotter than our Sun. Yet in the grand tapestry of the universe, it is just one of countless stars, each with its own unique story, contributing to the cosmic narrative. The beauty of the Hertzsprung-Russell diagram lies in its ability to reveal patterns in the cosmos. As stars evolve, they migrate off the main sequence, transitioning into different stages of their life cycles. Those that exhaust their hydrogen fuel will eventually become giants, shedding their outer layers and leaving behind a core that may become a white dwarf. The journey through the main sequence is but one chapter in the grand saga of a star's life, setting the stage for the dramatic transformations that follow. Reflecting upon the lives of these celestial bodies, we can't help but admire the outstanding individuals who have dedicated their lives to understanding them. Take, for instance, the renowned astronomer Annie Jump Cannon, who played a pivotal role in the development of the stellar classification system. Through her meticulous observations and classifications, she unveiled the underlying order of the stars, providing insight into their nature and behavior. Cannon's work exemplifies the intersection of science and artistry, revealing the elegance of the universe in a way that inspires both wonder and curiosity. The main sequence phase is a testament to the resilience and beauty of stars. They are not merely burning balls of gas, but rather dynamic entities that play an integral role in the cosmic ecosystem. Their light nourishes the worlds that orbit them, creating a sanctuary for life in the vastness of space. When we gaze up at the night sky, we are not just looking at distant points of light, we are witnessing the lifeblood of the universe, the very essence of creation unfolding before our eyes. In this serene yet vibrant phase, stars continue to captivate our imagination. They are the beacons of hope and stability, illuminating the dark voids of space. As we ponder the life of a main sequence star, we are reminded of our own place in this grand cosmic story. Each star, with its unique characteristics and journey, contributes to the wondrous spectacle of the universe. What mysteries do they hold? What secrets lie within their glowing hearts? As we explore these questions, we open ourselves to the infinite possibilities that the universe has to offer. The main sequence phase is not merely a state of existence. It is a harmonious balance of forces, a beautiful interplay between energy and gravity. As we continue our exploration of the stars, we will witness the transitions that occur as these radiant giants evolve and transform, leaving us to wonder about the fate of the celestial bodies that light our night sky. In the vast expanse of the main sequence, stars exhibit a remarkable array of characteristics that define their existence and influence their environments. Each star, while fundamentally similar in its reliance on hydrogen fusion, possesses unique properties that determine its luminosity, temperature, and size. These traits form the very essence of a star's identity, allowing astronomers to classify and understand the diverse tapestry of the cosmos. Consider the temperature of main sequence stars, which is closely tied to their mass. The surface temperature of these celestial bodies can vary dramatically, influencing the color of the light they emit. Hotter stars, often appearing blue or white, radiate their energy efficiently, with temperatures soaring to thousands of degrees. In contrast, cooler stars, which may glow in shades of red, exhibit lower temperatures, creating a mesmerizing spectrum of colors across the night sky. This colorful dance of light invites us to ponder: how does a star's temperature affect its life and the planets that may orbit it? The answer lies in the energy output and the conditions necessary for life. A star's luminosity, or intrinsic brightness, is another defining characteristic shaped by its mass and temperature. More massive stars, with their intense fusion reactions, shine with a brilliance that can outshine entire galaxies. Meanwhile, smaller stars, although less luminous, offer a steady glow that can sustain life on surrounding planets for billions of years. This interplay of luminosity and temperature creates a vivid portrait of the stars, illustrating the profound diversity that exists among them. The Hertzsprung-Russell diagram, a cornerstone of stellar classification, serves as a visual representation of these relationships. By plotting stars according to their temperature and luminosity, we can discern patterns and trends that reveal the underlying mechanics of stellar evolution. As we observe the main sequence on this diagram, a distinct diagonal band emerges, separating the hot, luminous stars from their cooler, dimmer counterparts. It is within this band that we find the majority of stars, including our own Sun, a prime example of a G-type main sequence star. As we contemplate the significance of the Hertzsprung-Russell diagram, we must acknowledge the contributions of those who have shaped our understanding of the cosmos. The work of astronomers such as Ejnar Hertzsprung and Henry Norris Russell laid the groundwork for this vital tool, allowing us to map the stars with precision. Their insights have illuminated the path of stellar evolution, offering a glimpse into the life cycles of these magnificent entities. While the main sequence phase is a time of stability, it is also a period of profound transformation. Stars do not exist in isolation. They are part of a dynamic ecosystem, influencing and being influenced by their surroundings. The energy emitted by main sequence stars fuels the formation of new stars and planets, creating a continuous cycle of birth and death in the universe. This raises an intriguing question. How do these stellar giants impact the worlds that orbit them? The gravitational pull and radiant energy of a star can significantly affect the atmospheres and climates of its planets, shaping the conditions for life. As we consider the lifespan of main sequence stars, we find a fascinating correlation between mass and duration. More massive stars consume their hydrogen fuel rapidly, resulting in shorter lifetimes filled with explosive brilliance. Conversely, smaller stars, like red dwarfs, burn their fuel more slowly, creating a serene glow that can persist for eons. Imagine this contrast as a cosmic clock, with the larger stars racing against time, while the smaller ones take a leisurely stroll through the ages. This difference invites us to reflect on the nature of existence itself. Is it the intensity of life that defines its value, or the quiet resilience found in endurance? In the heart of this stellar phase, we also find the importance of chemical composition. The elemental makeup of a star plays a crucial role in determining its properties and ultimate fate. Stars are not uniform in their composition. They contain varying amounts of metals, which influence their luminosity and spectral characteristics. As they age and evolve, stars enrich their surroundings with heavier elements through processes such as supernovae, seeding the cosmos with the building blocks of planets and life. The legacy of a star extends far beyond its main sequence phase. When a star exhausts its hydrogen fuel, it embarks on a new journey, evolving into a red giant or supergiant. This transition is marked by dramatic changes in its structure, as the core contracts and heats up, igniting helium fusion. The outer layers expand, often engulfing nearby planets in a dazzling display of cosmic transformation. This metamorphosis reveals a profound truth. The life of a star is a continuous cycle of creation and destruction, a reminder of the interconnectedness of all things in the universe. As we marvel at the main sequence phase, we are reminded of the beauty and complexity of these celestial bodies. They are not merely distant points of light, but rather dynamic entities that shape the cosmos around them. Each star tells a story, a narrative woven into the fabric of the universe, inviting us to explore the mysteries that lie within their luminous hearts. In this serene yet vibrant phase of existence, we are left with a sense of wonder. The stars, with their intricate balances of energy and gravity, serve as beacons of hope and stability in the vastness of space. They remind us of our own journey and connection to the universe. As we ponder the lives of these celestial giants, we are drawn into the cosmic narrative, eager to uncover the secrets that await us in the chapters yet to be written. Chapter 4: Red Giant Phase, Expansion and Transformation. As a star reaches the end of its stable main sequence phase, it begins to undergo dramatic changes, marking the transition toward the red giant phase. The triggers for this monumental shift are twofold: the depletion of hydrogen fuel in the core and the gravitational forces at play. Picture the once vibrant core of a star, where hydrogen atoms have been tirelessly fused into helium for billions of years. Eventually, this fuel runs low, and the balance between gravitational forces and radiation pressure begins to falter. The core starts to contract under its own weight, a process that is both inevitable and profound. As the core shrinks, it heats up, raising temperatures to levels that ignite a new phase of stellar evolution. Surrounding the core, hydrogen that remains is now subjected to increased pressure and temperature, initiating hydrogen shell burning. Imagine layers of gas, once dormant, now ignited by the growing heat from below. This shell burning becomes a furious furnace, creating a cocoon of energy that envelops the contracting core. As the star enters this tumultuous phase, it undergoes remarkable changes in size, temperature, and luminosity. The outer layers, once tightly bound, begin to expand dramatically. A star that may have once been modest in size transforms into a magnificent giant, swelling to several times its original diameter. Visualize a balloon being inflated, stretching, and distorting as it grows ever larger. This expansion can be so extreme that it engulfs the inner planets of its solar system, rendering them uninhabitable. Alongside this expansion, the temperature of the outer layers decreases, resulting in a distinct shift in color. The once brilliant yellow or white light of a main sequence star gives way to a softer, reddish hue, akin to the warm glow of a sunset. This transformation is not merely aesthetic, it signifies a deeper change within the star. The luminosity of the star also skyrockets, increasing dramatically as the energy produced by the hydrogen shell burning contributes to an ever-brightening exterior. In this new state, the star is no longer a stable beacon of equilibrium. It is a sprawling, luminous entity undergoing constant change and transformation. Imagine witnessing this spectacle, observing the vibrant colors and the sheer magnitude of a red giant star as it dominates the night sky. As the core continues to contract and heat up, the conditions become ripe for a new phase of nuclear fusion, the fusion of heavier elements. With temperatures soaring, helium atoms begin to collide and fuse, forming heavier elements such as carbon and oxygen. This process is often described as a stellar alchemy, where the very fabric of the universe is rewritten within the heart of a star. The fusion of these heavier elements is not only a testament to the star's evolution, but also a crucial step in the cycle of life and death within the cosmos. Renowned astrophysicist Carl Sagan once remarked, "The cosmos is all that is or ever was or ever will be." Within a red giant, this statement rings particularly true. The elements forged in the heart of these colossal stars will one day be scattered across the universe, seeding new stars, new planets, and perhaps even new life. But what does it mean for a star to become a red giant? It is a transformation steeped in both beauty and inevitability. As the outer layers continue to expand, the star's gravitational grip loosens, and its fate begins to intertwine with the very fabric of the cosmos. Each moment spent in this phase is a celebration of the star's life, a testament to the forces of nature that have shaped its journey. In this vast cosmic ballet, the story of a red giant unfolds, revealing the intricate processes that govern the universe. Each star is a unique narrative, a chapter in the grand book of existence. As we witness these transformations, we find ourselves pondering the profound questions of life, creation, and the interconnectedness of all things. The red giant phase is not a solitary event. It is a part of a greater cycle that echoes through the ages. The legacy of these stars is inscribed in the very elements that make up our own existence. Have you ever considered that the carbon in your own body may have originated in the core of a dying star? It is a humbling thought, reminding us of our place in the universe and the shared heritage we all possess. As we marvel at the beauty of a red giant, we must also acknowledge the forces at work behind its transformation. The processes of hydrogen shell burning and core contraction are not merely mechanical. They are the life force of the star, a testament to its resilience and adaptability. Even as the star expands and transforms, it remains in a state of flux, a reminder that change is the only constant in the universe. In essence, the red giant phase encapsulates the journey of a star from its stable existence to its eventual transformation. It is a period of growth, of radiant energy, and of profound changes that will ultimately lead to the star's final fate. The universe constantly whispers its secrets through these celestial bodies, inviting us to listen, to learn, and to reflect on the mysteries of existence. As the red giant draws on its remaining resources, it prepares for the next chapter in its life, one that will be marked by both beauty and destruction. The fusion of heavier elements holds the promise of new beginnings, even as the star itself approaches the end of its life cycle. What stories lie ahead for these magnificent stars? What wonders await us in the vastness of the cosmos? The journey of a star is both intricate and awe-inspiring, a dance of energy and matter that shapes the universe in ways we are only beginning to comprehend. The red giant phase serves as a poignant reminder of the cycle of life, the interconnectedness of all things, and the enduring legacy of stars that have come before us. Each transformation is a testament to the beauty of existence, a reminder that even in the face of change, there is a continuity that binds us all together. As we continue to explore the vast reaches of the universe, let us carry with us the knowledge that we are part of this grand narrative. The red giant phase, with its expansion and transformation, is not just a chapter in the life of a star. It is a reflection of our own journeys, filled with change, growth, and the promise of new beginnings. As the red giant phase progresses, the intricate dynamics of stellar evolution become even more compelling. The fusion of helium into heavier elements is not a singular event, but a continuing cascade of nuclear reactions that shapes the very essence of the star. Imagine the core, now a crucible of high temperatures and pressures, where helium nuclei collide with an intensity previously reserved for hydrogen. These collisions initiate a new form of fusion, creating carbon and oxygen, the building blocks for a multitude of celestial phenomena. This transitional phase is often marked by a significant change in the star's internal structure. The core becomes increasingly dense and hot, while the surrounding shells continue to burn hydrogen. The temperature at the core can reach levels so extreme that it ignites further fusion processes, allowing the star to evolve in ways that were once unimaginable. The fusion reactions create not just energy, but a rich tapestry of elements that will later contribute to the formation of planets and life itself. Notably, the famous physicist and cosmologist Stephen Hawking once said, "The only black hole that can't be observed is the one we all live in." In a sense, the core of a red giant represents a similar mystery, a hidden realm where the very elements essential for life are forged under conditions beyond our earthly comprehension. It is a reminder that even in the darkest corners of the universe, creation is continuously at work. But what happens when helium fusion becomes the predominant process? The answer lies in the star's evolutionary path, as it seeks to balance the increasing gravitational forces with the energy generated from these new fusion reactions. As the core contracts further, it heats up to a point where carbon fusion can commence, marking a significant milestone in the life of a red giant. This path to carbon fusion is not simply a linear progression. It is a complex interplay of forces, where each step forward is both a triumph and a precursor to the star's ultimate fate. Visualize the elements being created in the core as if they are the ingredients in a cosmic kitchen. Each collision and fusion reaction produces a new element, contributing to a stellar recipe that has been perfected over billions of years. At this stage, the star becomes a veritable factory of elements, crafting everything from carbon, which forms the basis of organic life, to oxygen, essential for respiration. As these heavier elements accumulate, they alter the physical characteristics of the star itself. The outer layers, now laden with new material, continue to expand, leading to further changes in luminosity and temperature. The intense energy produced by these fusion processes creates an outward pressure that counteracts the inward gravitational pull, allowing the star to maintain its form even as it transforms. This period of transformation can be likened to an artist adding layers to a canvas, with each stroke contributing to a more vibrant and complex picture. The star, once merely a yellow or white beacon, now radiates a spectrum of colors, reflecting its dynamic internal processes. The luminosity of a red giant swells to astonishing levels, illuminating the surrounding cosmic landscape. Imagine standing beneath a night sky alive with the glow of nearby red giants, their brilliance a testament to the energy being unleashed within. With each heartbeat of fusion, these stars not only shine brightly, but also serve as crucial beacons, guiding the formation of new celestial bodies in their wake. As the red giant continues its journey through the cosmos, it inevitably approaches a crossroads. The fusion of heavier elements like carbon and, eventually, neon creates a race against time. How long can the star sustain these processes? The answer is rooted in the star's mass and composition, determining how long it can continue fusing elements before it reaches a critical point. A point where it can no longer sustain the delicate balance between gravitational collapse and the energy produced from fusion. As the star exhausts its nuclear fuel, the outer layers will shed, creating stunning planetary nebulae that can be seen across vast distances. This spectacle is yet another reminder of the beauty and transience of stellar life. The echoes of these red giants will resonate throughout the universe, seeding the interstellar medium with the elements necessary for future generations of stars and planets. In this cosmic story, we find ourselves pondering the cycles of creation and destruction. What does it mean for a star to give birth to new life? When red giants finally expel their outer layers, they contribute to a galactic recycling program that enriches the universe with the very materials that comprise us. In the grand scheme of cosmic evolution, these stars are the architects of our existence, crafting the ingredients for life itself. Each transformation they undergo is a chapter in the story of the universe, a testament to the interconnectedness of all things and the continuous cycle of birth and rebirth that defines our reality. The journey of a red giant is a magnificent tapestry woven with threads of energy, matter, and time. It is a reminder that even in moments of great change, there is a profound beauty to be found in the unfolding of life's mysteries. As we reflect on the nature of these stars, we invite a deeper appreciation for the cosmos, where each stellar phase contributes to the grand narrative of existence, urging us to gaze upward and wonder at the vastness of our shared universe. Chapter 5: Late Stellar Evolution, Preparing for Death. As a star transcends the tumultuous red giant phase, it embarks on a journey marked by profound transformations. The core, now a bastion of helium, begins to undergo a new phase of nuclear fusion known as helium burning. This process is critical, for it is during this stage that the star forges carbon and oxygen, the fundamental building blocks for countless celestial bodies and, ultimately, life itself. Imagine the core of a star, once dominated by hydrogen fusion, now aglow with the energy of helium atoms fusing together in a delicate ballet. This is where the triple alpha process comes into play. It is a remarkable sequence of reactions where 3 helium nuclei, or alpha particles, collide under immense pressure and temperature. The first collision creates a beryllium nucleus, a fleeting and unstable entity. However, if another helium nucleus joins this intermediate form before it decays, carbon is born. This process does not merely produce carbon, it sets the stage for oxygen production as well. If conditions are just right, 2 carbon nuclei can also fuse, resulting in oxygen. This creation of carbon and oxygen is essential not just for the star itself, but for the universe at large. These elements will eventually find themselves woven into the very fabric of new stars, planets, and even the organisms that inhabit them. The implications of this transformation are profound, inviting us to ponder the interconnectedness of all things. What if the very atoms that make up our bodies were once part of a star blazing brilliantly in the cosmos? As we contemplate this cosmic cycle, it's fascinating to note that the late-stage evolution of a star is not a uniform process. Rather, it varies significantly based on the star's mass. For less massive stars, like our own Sun, the journey continues toward a gentle conclusion. After exhausting its helium fuel, the star will shed its outer layers, creating a spectacular display known as a planetary nebula. This shimmering cloud of gas and dust is a testament to the life of the star, a final gift to the universe. The core that remains, now a white dwarf, will gradually cool and fade over billions of years, leaving behind a legacy of enriched stellar material. Imagine this planetary nebula, a brilliant swirl of colors and light, spreading the remnants of the star across the cosmos. The gases and dust released during this phase contain not only helium, but also carbon, oxygen, and other heavier elements. These materials will eventually condense into new stars, planets, and perhaps even life forms. The cycle of creation continues, a dance of rebirth that echoes through the annals of time. Now consider the more massive stars. Their evolution takes a more dramatic turn. When a massive star exhausts its helium, it faces a relentless gravitational pull that leads to further fusion processes. These stars can fuse heavier elements, continuing the process until they reach iron in their cores. Iron fusion does not yield energy. Instead, it consumes it, heralding the final act of a massive star's life. The core collapses under its own weight, leading to a cataclysmic supernova explosion. In this moment, elements heavier than iron are forged in the explosive aftermath, scattering throughout the universe. This stark contrast in late stellar evolution between massive and less massive stars invites us to reflect on the diverse pathways of existence. What tales could the remnants of these stars tell if they could speak? The elements forged in their hearts have traveled vast distances, mingling in the cosmos, waiting for the right conditions to spark new life. As we witness these cosmic events unfold, we cannot help but marvel at the intricate balance of forces at play. The very process of stellar evolution is a testament to the universe's ability to create, destroy, and recreate. In the quiet moments between the stellar births and deaths, we find a soothing rhythm, a cosmic lullaby that beckons us to dream beyond the stars. The images of planetary nebulae and supernovae linger in the mind, painting a vivid picture of the universe's grand design. Each celestial event contributes to the ever-evolving story of the cosmos, a story that is not just about stars, but about everything that follows. The journey of stellar evolution is a reminder that life, in all its forms, is intricately linked to the stars. With each star that reaches the end of its life cycle, the universe breathes a sigh of renewal. The death of one star is the beginning of another. As planetary nebulae disperse into the interstellar medium, they serve as fertile grounds for new star formation. The cycle of life continues, with each generation of stars contributing to the richness and diversity of the cosmos. In the vastness of space and time, we find comfort in the knowledge that we are part of this grand narrative. The elements created in the hearts of stars resonate within us, connecting us to the very fabric of the universe. As we ponder our origins, we are reminded of the profound truth that we are all participants in this cosmic journey. As we transition from the vibrant hues of stellar birth to the somber beauty of stellar death, we experience a sense of closure and rebirth. the late stages of stellar evolution hold a mirror to our own existence, reminding us that every beginning carries within it the seed of an ending. Just as stars prepare for their final act, so too do we navigate our own journeys through life, embracing change and transformation. Imagine the warmth of a star's light, illuminating the darkness, a beacon of hope in the vast expanse of the universe. Though they may flicker and fade, the legacy of these celestial giants endures, echoing through the cosmos and into the hearts of those who gaze upon the night sky. In this way, the story of stellar evolution becomes a story of connection, a reminder of the beauty that lies within cycles of creation and destruction. As we reflect on the late stellar evolution, we find ourselves contemplating the nature of existence itself. The universe is not merely a backdrop for our lives. It is an active participant in the unfolding drama of creation. Each star, in its journey from birth to death, contributes to the greater tapestry of the cosmos, weaving together threads of light, energy, and matter that resonate with our very being. In this harmonious interplay of cosmic forces, we begin to understand that the end of a star's life is not an end at all, but rather a transformation. Just as we face our own endings, we are invited to consider the possibilities that lie beyond. The legacy of stars, their elements scattered across the universe, serves as a testament to the enduring cycle of life. As we close our eyes and drift into thoughts of the cosmos, may we carry with us the knowledge that we are part of this wondrous journey. Each star's life, each planetary nebula, and each supernova contributes to the rich narrative of existence. In the quiet moments of reflection, we embrace the beauty of our shared cosmos, finding peace in the knowledge that we are all connected through the very essence of the stars. As helium burning progresses within a star, we witness the birth of elements that will shape the universe for eons to come. The triple alpha process, a remarkable feat of cosmic engineering, not only creates carbon, but also allows for the synthesis of heavier elements in subsequent reactions. This intricate sequence of fusion events occurs under conditions of extreme temperature and pressure, making the core a crucible of creation. Visualize the core of a star, a seething mass where temperatures soar and densities pressurize. Here, in this stellar heart, the fusion of helium nuclei symbolizes a pivotal moment in the life of the star. This transformation is not just a scientific phenomenon, it is a metaphor for change, reflecting the broader narrative of existence. How often do we encounter moments of transformation in our own lives where the old gives way to the new? As the star continues its journey, the variations in late-stage evolution become apparent. For stars of different masses, the path diverges in fascinating ways. Less massive stars, like our familiar Sun, will ultimately embrace a gentle farewell. After exhausting their helium fuel, they will undergo a final phase of expansion and contraction, leading to the shedding of their outer layers. This process gives rise to a planetary nebula, a breathtaking spectacle that illuminates the night sky with vibrant colors as the remnants of the star disperse into the cosmos. Imagine the beauty of a planetary nebula, a kaleidoscope of gases and dust swirling gracefully through space. Each filament tells a story, a narrative of the star's life and its contributions to the universe. The elements forged within its core are released, enriching the interstellar medium and providing the building blocks for future generations of stars and planets. In this grand cycle, the remnants of one star become the cradle for another, a poignant reminder of the interconnectedness of all celestial bodies. Yet, for more massive stars, the conclusion is far more dramatic. These giants, having consumed their helium and forged heavier elements, confront a relentless gravitational collapse as they approach the end of their lives. This final act is a powerful reminder of the forces that govern the universe. When these stars reach the iron fusion stage, they are unable to sustain the fusion process that once fueled their brilliance. Instead, they succumb to gravity's inexorable pull, leading to a spectacular supernova explosion. In this cataclysmic event, the core implodes, resulting in a shockwave that ejects the outer layers into space. Picture a cosmic fireworks display, where the elements formed during the star's life are hurled into the void, scattering across the cosmos. This explosion not only marks the end of the star's existence, but also the genesis of new celestial bodies. In the aftermath, elements heavier than iron are created through rapid neutron capture, a process that occurs in the chaotic environment of a supernova. What might it be like to witness such an event? The sheer power of a supernova, the energy released in a single moment, is incomprehensible. It serves as a reminder of the fragility of existence and the beauty of creation through destruction. The very atoms that compose our world may have once been part of these explosive endings, forever linking us to the cosmos. As we reflect on these processes, we come to appreciate the complexity of stellar evolution. The stages of a star's life, from its formation in a nebula to its explosive end, illustrate a profound cycle of birth, death, and rebirth. Each star, regardless of its mass, contributes uniquely to this cosmic narrative. The remnants of less massive stars, in their gentle dispersal, contrast sharply with the violent finale of their more massive counterparts. In this vast tapestry of existence, we are reminded of the delicate balance that sustains life. The elements created within stars are not mere building blocks. They are the very essence of what connects us to the universe. As we ponder our origins, we are invited to consider the countless generations of stars that have come before us, each playing a role in the unfolding story of the cosmos. The concept of planetary nebulae invites us to imagine the beauty and fragility of life. As these luminous shells are formed, they serve as a reminder that endings can also be beginnings. The gases and dust released into the universe will coalesce once more, giving rise to new stars, planets, and perhaps even life itself. This cyclical nature of existence resonates deeply within us. Just as stars prepare for their eventual demise, we too must embrace change and transformation in our lives. Each moment we experience, whether joyous or sorrowful, contributes to our own personal evolution. How often do we reflect on the beauty found in these transitions? As we contemplate the late stellar evolution, we find solace in the knowledge that we are part of a greater cosmic journey. The stars above us are not distant points of light, but symbols of a shared existence. In our darkest moments, we can look up and remember that we are forged from the same elements that once burned brightly in the hearts of stars. In the quiet of the night, as we gaze up at the vast expanse of the universe, we are reminded that every ending carries within it the promise of a new beginning. The life cycles of stars mirror our own, inviting us to embrace the beauty of transformation. In this way, the late stages of stellar evolution become a comforting whisper, a soothing reminder that we are all part of something much larger than ourselves. Chapter 6: Supernova Mechanics, the Explosive Finale. As we explore the extraordinary finale of a star's life, we find ourselves on the precipice of a cosmic spectacle known as a supernova. This event is not merely an explosion. It is the culmination of a star's journey, a breathtaking release of energy that marks the end of its existence. But what conditions lead to such a cataclysmic event? For massive stars, the path to supernova is paved by the relentless march of time and the forces that govern stellar evolution. As a star exhausts its nuclear fuel, it enters a stage of instability. Imagine a once mighty giant whose energy has waned, struggling to maintain balance. The core, now dense and hot, is composed primarily of iron. Iron, while it may seem like a stable end product, is the harbinger of a star's doom, for it cannot release energy through fusion. As the core accumulates iron, it reaches a critical mass, a tipping point where pressure and temperature can no longer support the weight of the outer layers. At this juncture, the immense gravitational pull of the core becomes overwhelming. Picture a colossal weight crashing down, collapsing upon itself in a rapid, catastrophic implosion. This is the core collapse mechanism, the very heart of a type II supernova. The outer layers of the star rush inward, creating shock waves that will soon reverberate throughout the cosmos. Yet the core itself, now a neutron star or even a black hole, is transformed into a new state of matter, where the laws of physics behave in ways that challenge our understanding. Contrasting this, we have type I supernovae, which arise from a different set of circumstances. These explosions are often the result of binary star systems, where a white dwarf accumulates matter from a companion star. As it reaches a critical limit, known as the Chandrasekhar limit, the white dwarf ignites in a furious explosion. Can you imagine the violent release of energy when a star that has already passed through its life cycle reignites in such a spectacular fashion? In both cases, whether through core collapse or the ignition of a white dwarf, the supernova serves as a cosmic forge, creating elements that will be scattered across the universe, enriching the interstellar medium with the building blocks of new stars, planets, and perhaps even life. As we delve into the mechanics of these explosions, one cannot help but be awed by the sheer scale of energy released. A supernova can outshine entire galaxies for a brief moment, releasing more energy in a few days than the sun will emit over its entire lifetime. Imagine that, a single event, a flash of brilliance that illuminates the darkness, a reminder of the immense power contained within the universe. The shockwaves generated by a supernova are not mere ripples. They are massive cosmic waves that travel through space. These waves interact with surrounding gas and dust, compressing and heating it, leading to the formation of new stars. The remnants of a supernova, often referred to as a supernova remnant, can continue to expand for thousands of years, creating magnificent nebulae that glow with the light of newly formed stars. Let us pause for a moment to consider the people who have dedicated their lives to understanding these phenomena. Among them is the renowned astronomer Adam Rees, who has contributed significantly to our comprehension of the universe's expansion. He once remarked, "The universe is a grand tapestry of interconnected events, and supernovae play a vital role in weaving that tapestry." Each supernova is not only an end, but also a beginning, a crucial point in the life cycle of cosmic matter. As we visualize this process, imagine the grandeur of a celestial explosion. The outer layers of the star, propelled outward by the intense force of the shockwave, create a spectacular display of light and energy. The elements forged in the heart of the star are scattered into the vastness of space. Elements like carbon, nitrogen, and oxygen, essential for life as we know it, are cast into the universe, ready to be woven into new celestial bodies. The aftermath of a supernova is a cosmic recycling process, a reminder of the cyclical nature of existence. It is remarkable to think that the very atoms that make up our bodies could have once been part of a star that exploded eons ago. The universe operates on a grand scale of creation and destruction, where endings are intertwined with beginnings. This is the essence of stellar evolution. As we continue to reflect on the intricate dance of life and death among the stars, we see that supernovae are not simply cataclysmic events. They are transformative. They play a vital role in the evolution of galaxies and the cosmos itself, seeding the universe with the materials necessary for the next generation of stars. The energy released during a supernova is staggering. Imagine the shockwave traveling through space at incredible speeds, compressing the interstellar medium in its path. This compression leads to the formation of dense regions that can collapse to form new stars. The cycle of stellar life continues, driven by the remnants of those that have come before. Would you not marvel at the idea that with each supernova, we witness the universe's creative power, its ability to regenerate and renew? Each explosion is a testament to the forces that shape our universe, and we are all part of this grand narrative. As we delve deeper, we recognize that the remnants of supernovae can take on various forms. Some become pulsars, spinning rapidly and emitting beams of radiation, while others may collapse into black holes, regions of spacetime where gravity is so intense that nothing can escape. Can you imagine the awe-inspiring sight of a neutron star, its surface only a few kilometers across, yet containing more mass than our sun? The laws of physics become beautifully strange in these extreme environments. The legacy of supernovae extends far beyond their immediate explosion. They influence the formation of galaxies, the distribution of elements, and even the dynamics of dark matter. The energy and materials released help to trigger star formation in surrounding regions, leading to the birth of new stars and the continuation of the cosmic cycle. In reflecting on this profound connection, we come to appreciate that supernovae are not merely ends, but pivotal moments in the evolutionary story of the universe. Each explosion, each shockwave, is an invitation to witness the interplay of destruction and creation that defines our cosmic home. As we prepare to journey further into the complexities of stellar phenomena, let us carry with us the awe of the explosive finale that is a supernova. It is a reminder that we are part of a grander scheme, where every end leads to a new beginning, and where the remnants of the past continue to shape the future of the cosmos. As the core of a massive star succumbs to gravity, the collapse ignites a series of rapid and violent events, culminating in the explosive birth of a supernova. This cataclysmic finale is marked by a delicate interplay of forces, gravity pulling inward, while the pressure from nuclear reactions pushes outward. This is where the journey of type II supernovae takes shape, originating from the remnants of massive stars that have exhausted their nuclear fuel. Imagine the core, once a vibrant furnace of nuclear reactions, now a dense mass of neutrons and protons. The outer layers, unable to withstand the gravitational pull, begin their rapid descent toward this collapsing heart. As they fall, they gain speed, building up an incredible amount of kinetic energy. When these layers finally reach the core, they collide with such force that they rebound outward in a shock wave, propelling the outer envelope of the star into the cosmos. This shock wave is not simply a wave of energy. It is a herald of rebirth, scattering elements forged in the star's core across the universe. Type I supernovae, on the other hand, arise from a different origin. Picture a binary star system where a white dwarf, the remnant of a star that has already undergone its own cycle of life and death, siphons material from a companion star. As it gathers mass, it approaches a critical threshold. When it surpasses this limit, an uncontrollable chain reaction ignites. The result is a powerful explosion, one that obliterates the white dwarf completely, leaving no remnant behind. This is the beauty of stellar life, a cycle where even the remnants of stars can give rise to spectacular displays of energy and light. The differences between these two types of supernovae highlight the varied paths that stars can take as they reach their end. While type II supernovae provide a vivid spectacle of a star's violent death, type I supernovae serve as cosmic beacons, helping astronomers gauge the vast distances of the universe. Each explosion brings with it a wealth of information, a moment captured in time that speaks of the universe's history and structure. Let us consider the energy released during these events. The sheer magnitude is staggering, a release of energy equivalent to that produced by hundreds of millions of suns in a matter of days. This energy is what drives the shockwave into the surrounding space at phenomenal speeds. As the shockwave propagates, it compresses the interstellar medium, creating regions of high density. These regions become fertile grounds for the formation of new stars, continuing the cycle of life that began eons ago in the heart of nebulae. In the wake of a supernova, the remnants can become a supernova remnant, a complex and beautiful structure filled with glowing gas and dust. The Crab Nebula, for instance, is a famous remnant of a supernova observed in the 11th century. Within it, we can see the remnants of the exploded star, glowing with the energy of newly formed elements and the pulsating heartbeat of a neutron star at its center. This cosmic tableau serves as a reminder of the intricate processes at play, continuously shaping our universe. As the shockwave travels outward, it interacts with the surrounding material, creating a network of new stars and planetary systems. One cannot help but marvel at the elegance of this cosmic recycling. The elements that once formed the very essence of a star are now being incorporated into new formations, a symbiotic relationship that echoes throughout time. Think of the words of the astronomer Carl Sagan, who once expressed, "The cosmos is all that is or ever was or ever will be." This profound sentiment speaks to the interconnectedness of all celestial phenomena, where each supernova contributes to the ever-expanding narrative of the universe. As we ponder this cosmic interplay, it is essential to recognize the role of these explosions in the grand narrative of cosmic evolution. Supernovae not only enrich the universe with heavy elements, but also influence the dynamics of galaxies. The shock waves can trigger the formation of new stars, altering the very fabric of galactic structure. This complex dance of creation and destruction illustrates the universe's ability to perpetuate itself, fostering new life from the ashes of the old. In reflecting on the legacy of supernovae, we are reminded that these explosive finales are not merely conclusions, but integral components of a larger cosmic cycle. The echoes of their energy reverberate throughout space, shaping the destinies of countless stars yet to be born. Can you imagine the multitude of stars and planets that will rise from the remnants of a single supernova? Each one is a testament to the cycles of life and death, where every end heralds a new beginning. As we absorb the significance of these celestial events, we recognize that supernovae serve as more than just markers in the life of stars. They are a bridge to understanding the processes that govern our universe, revealing the intricate relationships that bind all matter. From the formation of new stars to the dispersal of elements that form planets, supernovae play a crucial role in the ongoing saga of the cosmos. As we continue our exploration, let us carry with us the wonder of these explosive events. They remind us of the magnificent forces at play, shaping not only the universe around us, but also the very atoms that make up our existence. Each supernova is a celebration of the universe's boundless creativity, an invitation to ponder our place within this grand cosmic narrative. Chapter 7: Neutron Stars and Black Holes, Stellar Remnants. In the aftermath of a supernova, the universe is left with remnants that can ignite the imagination and evoke a profound sense of wonder. Among these stellar remnants, neutron stars and black holes represent the extremes of cosmic evolution and the ultimate fate of massive stars. When a massive star exhausts its nuclear fuel, it undergoes a cataclysmic explosion that is a supernova. This explosive finale does not merely mark the end of a star's life. It is a transformative event that creates neutron stars. Picture the remnants of this explosion, where the outer layers of the star are blasted into space, while the core collapses under its immense gravitational force. In this collapse, protons and electrons are crushed together to form neutrons, resulting in a compact object that is incredibly dense. A neutron star is so dense that a sugar cube-sized amount of its material would weigh as much as an entire mountain on Earth. Imagine this celestial body, a neutron star, spinning rapidly on its axis. As it does, it emits beams of radiation from its magnetic poles. These beams sweep across space like a cosmic lighthouse. When they align with Earth, we perceive them as pulsating signals, leading to the discovery of pulsars, rotating neutron stars that emit regular pulses of radiation. The first pulsar was discovered in the late 1960s by Jocelyn Bell Burnell, a pivotal moment that opened new avenues in astrophysics. She once remarked, "The discovery of pulsars was a bit like finding a lighthouse in the middle of the ocean. You don't know where you are, but you know there is something out there." This discovery has since provided insights into the nature of gravity, time, and the fundamental structure of the universe. Neutron stars are not just fascinating because of their density and rapid rotation. They also exhibit extraordinary magnetic fields, trillions of times stronger than Earth's. Such immense fields warp the very fabric of space around them. Can you imagine the interplay of gravity and magnetism in such extreme conditions? The surface of a neutron star is a place where the laws of physics, as we know them, begin to blur. The surface temperature can reach millions of degrees, causing it to glow in X-ray wavelengths, revealing the secrets of its violent past to astronomers. As we ponder the journey of a massive star, we encounter another possibility that arises from the remains of a supernova: black holes. When the core of a massive star collapses, it can continue to compress beyond the neutron star stage, leading to the formation of a black hole. But what conditions lead to this transformation? For a black hole to form, the core must exceed a critical mass, the limit beyond which neutron degeneracy pressure can no longer support the star against gravitational collapse. This is known as the Tolman-Oppenheimer-Volkoff limit. Imagine the core compressing under its own weight, where not even light can escape its gravitational pull. This boundary is known as the event horizon. Crossing this threshold means venturing into a realm where the familiar laws of physics cease to apply in the way we understand them. Once something crosses the event horizon, it is lost to the universe, forever shrouded in darkness. What lies beyond this boundary? It remains one of the great mysteries of science. At the heart of a black hole lies the singularity, a point where matter is thought to be infinitely dense and gravity is infinitely strong. Here, our understanding of space and time breaks down. The singularity is often described as an enigma, a region where the mathematics of general relativity and quantum mechanics clash. It raises questions about the very nature of reality. What happens to the fabric of space and time in such an extreme environment? The existence of black holes challenges our perceptions of the universe. They are not just cosmic vacuum cleaners, they can influence the orbits of stars and the motion of galaxies. When a black hole is part of a binary system, it can draw matter from its companion star, creating an accretion disk that radiates energy in the form of X-rays, making them some of the most energetic objects in the cosmos. As we explore these stellar remnants, we are reminded of the cosmic cycle of creation and destruction. Neutron stars and black holes are not endpoints. They are integral components of the universe's ongoing evolution. They serve as laboratories for understanding the fundamental forces that govern existence. When we look up at the night sky, We are not merely gazing at distant points of light. We are witnessing the aftermath of stellar evolution, a cosmic saga that continues to unfold. These remnants inspire curiosity and wonder, compelling us to ask deeper questions. How do these extreme conditions affect our understanding of gravity, time, and the structure of space? Imagine standing on the surface of a neutron star, feeling the immense gravitational force pulling you down. Or picture yourself at the event horizon of a black hole, staring into the void where no light escapes. The study of neutron stars and black holes not only enriches our understanding of the universe, but also connects us to the very fabric of existence. They remind us that the cosmos is filled with mysteries waiting to be unraveled, and that every discovery brings us closer to understanding our place in this vast, awe-inspiring universe. The heart of a black hole is a place of unfathomable mystery, where conventional understanding falters and the very essence of reality seems to unravel. Here, at the singularity, the fabric of space-time is thought to be infinitely warped, creating a point where density reaches unimaginable heights. In such an environment, the known laws of physics, as described by Einstein's theory of general relativity, collide with the principles of quantum mechanics. This intersection of theories leaves scientists grappling with profound questions. What happens to the information that falls into a black hole? Does it truly vanish, or is it somehow preserved? The event horizon, surrounding the singularity, serves as a one-way boundary. Crossing this threshold means entering a realm where escape is impossible, not even for light itself. Imagine standing at the edge of this boundary, peering into the abyss, where time itself behaves differently. To an observer hovering just outside the event horizon, it appears as if time slows down for anything approaching it. However, for the object falling in, the experience is quite the opposite, a journey toward an inescapable fate. Consider the implications of this phenomenon. Could it be that the information consumed by a black hole is not lost, but rather transformed? This question led to the development of theories such as the holographic principle, suggesting that all the information contained within a volume of space can be represented as a two-dimensional surface. It is a tantalizing idea, hinting at a deeper connection between the cosmos and the nature of reality itself. As we contemplate black holes, it is essential to recognize their role in the larger cosmic narrative. These enigmatic entities are not merely the remnants of dead stars. They are dynamic players in the evolution of galaxies. Supermassive black holes, residing at the centers of most galaxies, exert a gravitational influence that shapes the orbits of stars and the structure of galactic formations. They are like the gravitational anchors of the universe, pulling matter toward them and creating accretion disks that radiate energy across the cosmos. The accretion process transforms the surrounding material into a luminous disk of gas and dust, spiraling ever closer to the event horizon. This disk can reach staggering temperatures, emitting X-rays that provide valuable insights into the nature of black holes and their environments. Observations of these X-ray emissions have led to groundbreaking discoveries, revealing the presence of supermassive black holes in the centers of galaxies, and helping to establish a connection between black holes and the formation of galaxies themselves. The study of neutron stars and black holes continues to evolve, fueled by the relentless curiosity of scientists. The advent of gravitational wave astronomy has opened new pathways for exploration, allowing us to detect the ripples in space-time caused by the merging of black holes and neutron stars. Imagine the excitement of researchers as they capture these elusive signals, providing a glimpse into the dynamic interactions of these cosmic giants. With each detection, we uncover more about the violent processes that govern our universe, piecing together the puzzle of stellar evolution in ways previously thought impossible. Among the outstanding figures in this field is Kip Thorne, whose work on black holes has profoundly influenced our understanding of these cosmic phenomena. He once remarked, "If you want to make an apple pie from scratch, you must first create the universe." This playful yet profound statement captures the essence of scientific inquiry, emphasizing the intricate connections between the cosmos and the everyday world. As we immerse ourselves in the study of neutron stars and black holes, we come to appreciate the delicate balance of creation and destruction at play in the universe. These stellar remnants are not just the final acts of dying stars. They embody the cycles of rebirth that define the cosmos. In their wake, they forge the elements that will one day give rise to new stars and planets, perpetuating the cycle of existence. Each black hole and neutron star serves as a reminder of the intricate dance between matter and energy, gravity and radiation. They compel us to ponder our own existence, urging us to look deeper into the fabric of the universe. What lies beyond the singularity? What mysteries does the event horizon guard? With every question, we find ourselves drawn into a cosmic quest, one that not only seeks to understand the forces shaping our universe, but also to connect us to the very essence of existence itself. As we gaze into the night sky, we are reminded of the interconnectedness of all things. The light we see is a testament to the life cycles of stars, each twinkling point harboring stories of creation, transformation, and ultimately, the profound mysteries that remain just beyond our reach. The universe invites us to explore its depths, to question, to wonder, and to seek answers to the questions that have captivated humanity for generations. In this grand journey, neutron stars and black holes stand as the ultimate enigma, challenging us to expand our understanding and embrace the unknown. As we continue to unravel the secrets of these stellar remnants, we find ourselves not only as observers of the cosmos, but as active participants in its unfolding narrative. Through our pursuit of knowledge, we forge a connection to the universe, illuminating the path toward understanding our place within this vast, awe-inspiring expanse. As we shift our focus from the explosive finale of a supernova, we delve deeper into the fascinating characteristics and properties of neutron stars. These compact remnants, born from the collapse of massive stars, are true marvels of the universe. Imagine a sphere with a radius no larger than a city, yet containing more mass than our Sun. This extraordinary density is a result of the collapse, where neutrons are packed tightly together, creating a state of matter unlike anything found on Earth. Neutron stars are extraordinarily unique not only for their size, but also for their extreme physical conditions. The surface gravity on a neutron star is so intense that if you were to drop an object from a height of just 1 meter, it would accelerate toward the surface at speeds that would be fatal. Picture this. An object weighing a mere kilogram on Earth would weigh several billion kilograms on a neutron star. The composition of neutron stars is equally remarkable. The outer crust consists of a solid lattice of atomic nuclei, while beneath this lies a liquid core of superfluid neutrons. Imagine the strange dance of particles in this core, where neutrons move without friction, allowing them to flow freely and create a unique state of matter. This phenomenon raises intriguing questions about the nature of matter itself and how it behaves under such extreme conditions. Additionally, neutron stars are often accompanied by intense magnetic fields, which can be trillions of times stronger than Earth's own field. This magnetic intensity leads to fascinating effects, such as the emission of high-energy gamma rays and X-rays. When a neutron star spins, its magnetic field can produce powerful jets of radiation that shoot out into space. Picture a lighthouse, but instead of a beam of light, it is a beam of high-energy particles, illuminating the cosmos in a dazzling display of energy. In the realm of black holes, the transition from a neutron star to this enigmatic entity occurs under very specific conditions. When the remaining core of a massive star exceeds the Tolman-Oppenheimer-Volkoff limit, even the degeneracy pressure of neutrons can no longer withstand the relentless force of gravity. This transition marks a pivotal moment in stellar evolution, leading to the formation of a black hole. Consider the implications of this transition. Once a black hole forms, it creates a gravitational field so powerful that it warps the very fabric of spacetime around it. Imagine a smooth, flat sheet of fabric, representing spacetime, suddenly being punctured by a heavy ball. The ball represents the black hole, creating a well that draws everything nearby into its depths. This visualization helps to illustrate the nature of the event horizon, an invisible boundary surrounding the black hole, beyond which escape is impossible. The event horizon serves as a delineation between the known universe and the unknown. Crossing this threshold transforms the nature of reality itself, as time and space behave in ways that defy our everyday experiences. For an observer far from the black hole, it appears as if time slows down for anything approaching the event horizon. Yet, for the object crossing it, the experience is a swift plunge into a realm of darkness and mystery. At the singularity, the heart of the black hole, our current understanding of physics reaches its limits. Here, matter is compressed into an infinitely dense point, where the laws of physics as we know them cease to function coherently. It is a place of paradox and enigma, where questions about the nature of reality become more pronounced. What does it mean for gravity to become so powerful that it overwhelms all other forces? What does it imply for our understanding of time, space, and existence itself? These questions have captivated some of the greatest minds in science. Stephen Hawking, a luminary in the field of theoretical physics, once stated, "The black hole is a place where the laws of physics break down." His work on black holes and the nature of singularities has profoundly influenced our understanding of the cosmos, emphasizing the need for a unified theory that encompasses both quantum mechanics and general relativity. As we contemplate the nature of black holes, we can also explore their role in the broader cosmic landscape. They are not mere endpoints, they are integral to the life cycle of galaxies. Supermassive black holes, residing at the centers of galaxies, can affect the formation and evolution of stars and planetary systems. They play a crucial role in the dynamics of galaxies, influencing their structure and behavior through their immense gravitational pull. Imagine a galaxy as a bustling city, with stars as the inhabitants. The supermassive black hole at the center acts as an unseen force, guiding the orbits of stars and shaping the trajectory of the galaxy's evolution. The interplay between black holes and their host galaxies is a dance of cosmic proportions, revealing the interconnectedness of all things in the universe. In this exploration of neutron stars and black holes, we are reminded of the cyclical nature of the cosmos. The remnants of dying stars give rise to new phenomena, shaping the universe in ways we are only beginning to understand. Each discovery unravels layers of complexity, inviting us to look deeper into the fabric of existence and ponder the ultimate fate of these celestial objects. As we stand on the precipice of knowledge, the mysteries of neutron stars and black holes beckon us to continue our journey of discovery. They challenge our perceptions and inspire us to delve into the unknown, urging us to seek answers to the questions that lie just beyond our reach. In this quest for understanding, we find ourselves connected to the universe, woven into the very fabric of its existence. Chapter 8, Stellar Nucleosynthesis, elements of the universe. In the heart of every star, a magnificent process unfolds, where elements are forged in the fiery crucible of nuclear fusion. These celestial bodies, radiant and eternal, create not only light but also the very building blocks of the universe. As stars live and die, they produce a rich variety of elements, each one destined to be scattered across the cosmos, enriching the very fabric of existence. Imagine for a moment the vast universe filled with stars, each one a cosmic forge. Within these stellar hearts, hydrogen atoms collide and fuse, turning into helium and, in the case of more massive stars, forging heavier elements such as carbon, oxygen, and beyond. This process of stellar nucleosynthesis is crucial, as it lays the groundwork for the elements that will one day form planets, life, and everything we know. Every glowing star is a reminder of this intricate ballet, a testament to the transformations occurring in their cores. As stars evolve, their life cycles take them through various stages, each marked by unique processes of element creation and distribution. When stars reach the end of their life, particularly those of significant mass, they explode in a spectacular fashion known as a supernova. This cataclysmic event does not simply mark the death of a star, it serves a far more profound purpose. Supernovae act as cosmic recyclers, hurling elements forged in their cores across the universe. Picture the remnants of an exploded star, scattering precious metals and gases into the void, seeding new nebulae and, eventually, new stars. The implications of these explosions are immense. It is through supernovae that elements heavier than iron are created, such as gold, silver, and uranium. The famous astronomer Carl Sagan once remarked on this cosmic connection, noting that the cosmos is all that is or ever was or ever will be. In this context, supernovae are the engines of cosmic evolution, fueling the cycle of creation and destruction that characterizes the universe. To truly appreciate the role of these explosive events, let us consider the concept of mass. The mass of a star significantly influences its life cycle and the types of elements it can produce. Smaller stars, like our Sun, will primarily burn hydrogen and helium throughout their lives, eventually shedding their outer layers and leaving behind a carbon-oxygen core. In contrast, massive stars undergo a more complex series of nuclear reactions, forming a rich variety of elements before their spectacular demise. The journey of a massive star culminates in a supernova, where the immense gravitational forces and temperatures enable the synthesis of the heaviest elements. What then is the connection between the stars and the origins of life on Earth? It is a question that evokes wonder and curiosity. The elements that compose our very bodies were once forged in the hearts of stars. Carbon, nitrogen, oxygen, and phosphorus, essential building blocks of life, were created through processes in these ancient giants. When supernovae exploded, scattering these elements across the cosmos, they eventually coalesced into new stars and planets, including our own. Picture Earth, a vibrant blue planet, rich with life, birthed from cosmic debris. The very air we breathe, the water we drink, and the complex organic molecules that comprise our cells owe their existence to the stellar processes that occurred long before our planet formed. The connection is profound and beautiful, revealing a universe that is not just a backdrop to human existence, but an intricate web of interrelated elements and forces. As we contemplate the journey of stars and their elemental creations, we are reminded of the cyclical nature of the universe. Stars are born, they live, and they die, but in their passing, they enrich the cosmos, contributing to an ever-evolving celestial landscape. The cycle of stellar nucleosynthesis is a reminder that we are part of something far greater, a cosmic continuum where every atom of our being has a story that stretches back to the very dawn of the universe. The exploration of stellar nucleosynthesis invites us to reflect on our place within this vast cosmos. As we gaze at the night sky, we are witnessing the light of distant stars, perhaps those that have already met their end. The light that reaches us may carry with it the essence of long-forgotten elements, remnants of a cosmic history that continues to unfold. In this grand narrative, the stars are not merely distant points of light. They are the architects of the universe, shaping the elemental landscape that allows life to flourish. As we embrace this understanding, we find ourselves intertwined with the cosmos, connected by the very elements that form the fabric of our existence. The stars, in their brilliance and eventual demise, are the storytellers of the universe, weaving a tale that is as old as time itself and as boundless as the sky above. The beauty of this process lies not only in its complexity, but also in its simplicity. Stars create, transform, and give life through their death, reminding us of the delicate balance that governs existence. Just as nature recycles, so too do the stars offer a lesson in renewal and transformation, a cycle that mirrors the rhythms of life on Earth. As we ponder these concepts, we are invited to consider our own journeys, reflecting on how we, too, are shaped by the elements of the universe. In the end, the story of stellar nucleosynthesis is one of creation, destruction, and rebirth. It is a reminder that we are all part of this cosmic dance, forever intertwined with the stars that bore us. As we explore the mysteries of our universe, may we continue to find solace in the knowledge that we are, indeed, made of stardust, shaped by the very forces that govern the cosmos. As we delve deeper into the intricate workings of stellar nucleosynthesis, we encounter the notion that stars are not merely celestial objects, they are intricate factories of elements. Each star, in its unique life cycle, contributes to the cosmic inventory, and this process is one of the universe's most remarkable phenomena. Imagine the vast, swirling dance of particles within a star's core, where the fusion of lighter elements gives birth to heavier ones, all governed by the laws of physics that have remained unchanged since the dawn of time. The life of a star is not just about its own existence, it is intimately tied to the universe's grand narrative. For instance, in the final throes of a star's life, the elements formed within its heart are expelled into the cosmos during a supernova. This expulsion is not random. It is a calculated release of energy and matter, akin to a mother nurturing her offspring by scattering seeds across fertile ground. Each seed carries the potential for new life, new stars, planets, and ultimately, life itself. The importance of supernovae in this cosmic recycling process cannot be overstated. These explosive events are responsible for dispersing the very elements that will later coalesce into new celestial bodies. Consider the role of a supernova as akin to a cosmic gardener, sowing the seeds of existence across the universe. As supernova remnants drift through the void, they encounter the dense clouds of gas and dust, merging and interacting in a symphony of creation, leading to the birth of new stars. The fate of these stars often depends on their mass, a crucial factor that dictates not only their lifespan, but also the types of elements they can create. Massive stars, for example, are capable of synthesizing elements up to iron through a series of fusion processes that occur in their cores. Beyond iron, however, the story shifts. The creation of heavier elements requires the extraordinary conditions found only in the cataclysmic aftermath of a supernova. Here, the intense heat and pressure allow for the rapid neutron capture process, known as the R process, which produces elements such as gold and uranium. Can you imagine the moment when these heavy elements are born, forged in the chaos of an exploding star, and sent forth into the universe? The connection between these elements and the origins of life on Earth is profound. The very building blocks of our existence were birthed in stars that lived and died long before our planet took shape. Carbon, nitrogen, and oxygen, all essential for life, were created through stellar processes and later scattered across the cosmos during supernovae. Picture the early Earth, a molten landscape enriched with these elements, waiting for the right conditions to foster life. As the planet cooled, these elements began to interact, leading to the formation of complex organic molecules. Isn't it fascinating to consider that the oxygen we breathe and the carbon that forms the basis of our very cells were once part of distant stars? This connection emphasizes that we are not separate from the universe. Rather, we are an integral part of its ongoing story. The famous astrophysicist Neil deGrasse Tyson eloquently captured this essence. The atoms in your body are traceable to stars that exploded and scattered their enriched guts across the universe. As we gaze at the night sky, we are witnessing the remnants of this cosmic history. The light from stars that twinkle above us may be millions of years old, carrying with it the stories of their birth and death. Each twinkle is a reminder of the transformative processes that have shaped not only the cosmos, but also our very existence. As we reflect on the cyclical nature of stellar life and death, we can appreciate the eternal flow of elements through the universe. This cosmic recycling is a testament to the interconnectedness of all things. Just as stars give life through their explosion, they also serve as a reminder of the fragility and beauty of existence. The universe is engaged in a continuous process of creation and destruction, a rhythm that echoes throughout the cosmos. In contemplating the vastness of time and space, one must wonder, what will become of the elements forged in our own sun when it, too, reaches the end of its life? As it transitions into a red giant, it will shed its outer layers, creating a planetary nebula. The remaining core, a dense white dwarf, will slowly cool over billions of years. The elements released during this process will eventually become part of the interstellar medium, ready to be drawn into new stars, planets, and perhaps even new life forms. The elements in our bodies, the air we breathe, and the very water that sustains us are a testament to this eternal cycle. Life, as we know it, is a continuation of the stellar processes that began billions of years ago. Each heartbeat, each breath we take, resonates with the rhythm of the universe. As we continue to explore stellar nucleosynthesis, let us carry with us the understanding that we are part of something magnificent. The stars are not just distant suns, they are our ancestors, the creators of the very elements that compose our existence. In every atom, there lies a story of cosmic birth, transformation, and rebirth. What is it that makes us feel so deeply connected to the cosmos? Perhaps it is the realization that we are all made from the remnants of stars, a truth that unites us with the universe in a profound way. We are participants in this grand cosmic play, where the stars are the protagonists, and we are but humble witnesses to their luminous saga. In the vast expanse of the universe, each star, each supernova, and each element serves as a reminder of the intricate web of existence. As we ponder these celestial phenomena, may we find comfort in knowing that we are not merely inhabitants of Earth but cosmic beings, intertwined with the fabric of the universe itself. Each moment, each breath we take, is a continuation of the celestial journey that began long before us and will continue long after we are gone. Chapter 9: Impacts on Galactic Evolution, Stars Shaping Worlds. Stars are more than mere points of light scattered across the vast darkness of the universe. They serve as the very catalysts for galaxy formation, shaping the cosmic landscape in profound ways. Imagine the birth of a galaxy, a colossal swirl of gas and dust, where the gravitational pull of emerging stars begins to sculpt the very fabric of the cosmos. As these stars ignite, they forge connections, drawing in surrounding matter and initiating the intricate dance of galactic evolution. The process of galaxy formation begins with the collapse of gas clouds, spurred on by the gravitational forces at play. These clouds, rich in hydrogen and helium, are the breeding grounds for stellar creation. Picture a serene, swirling nebula, where pockets of dense material coalesce to form the first stars. As these stellar giants awaken, they not only illuminate their surroundings, but also influence the matter around them, initiating a cascade of events that will birth entire galaxies. In this cosmic nursery, the energy released by new stars begins to heat the surrounding gas, causing it to collapse under its own gravity. This phenomenon illustrates the interconnectedness of stars and galaxies, demonstrating that the emergence of one can lead to the birth of many. As astrophysicist Carl Sagan once eloquently stated, "The cosmos is all that is or ever was or ever will be." The life of a star profoundly impacts the cosmic evolution of galaxies. As stars evolve, they engage in a remarkable transformation, influencing the material that surrounds them and the very structure of their galaxies. This influence is particularly evident during the violent end of a star's life, when supernovae occur, acting as both the death knell for the star and a catalyst for the birth of new stars. Supernovae are not merely explosions, they are cosmic fireworks that release vast amounts of energy and matter into the universe. Imagine a brilliant flash of light, brighter than an entire galaxy, as a massive star reaches the end of its life cycle. This cataclysmic event ejects elements synthesized during the star's lifetime, elements that are critical for the formation of new stars, planets, and even life itself. The shock waves from these supernovae compress nearby gas clouds, triggering the formation of new stars. It is a beautiful cycle of destruction and creation, where the end of one star paves the way for the beginnings of others. Consider the words of renowned astrophysicist Neil deGrasse Tyson, who suggested that we are all connected to each other biologically, to the Earth chemically, to the rest of the universe atomically. Each supernova enriches the interstellar medium with heavy elements, creating a fertile environment for new stars to form, thus continuing the cycle of cosmic evolution. As stars interact with dark matter, the mysterious substance that makes up a significant portion of the universe, they further influence the galactic landscape. Dark matter, which does not emit, absorb, or reflect light, exists as an invisible web that shapes the structure of galaxies. Imagine this dark matter halo surrounding galaxies, providing the gravitational scaffolding necessary for their formation. As stars evolve, their mass and gravitational pull interact with this dark matter, helping to steer the dynamics of the galaxy itself. What would happen if this dark matter were to vanish? The gravitational forces that bind stars to their galaxies would weaken, leading to a disintegration of galactic structures. The interplay between stars and dark matter is a delicate balance, one that ensures the stability and longevity of galaxies over cosmic timescales. The evolution of stars also plays a crucial role in the development of planetary systems. As stars progress through their life cycles, they shed material and redistribute elements throughout their surroundings. When a star enters the red giant phase, for instance, it expands dramatically, releasing layers of gas and dust into space. This material can coalesce and form new planetary systems. Imagine a once dominant star, now transformed and shedding its outer layers. This material, rich in the elements forged in the star's core, becomes the building blocks for planets. The cycle of stellar evolution thus intertwines with the formation of worlds, as cosmic debris from one star's death contributes to the birth of another generation of celestial bodies. The influence of stellar evolution on planetary systems is profound. The environments around stars can vary drastically based on their mass and stage of life. For example, a massive star may forge heavier elements in its core, enriching the surrounding material with the necessary components for terrestrial planets. In contrast, smaller stars produce lighter elements, shaping a different kind of planetary system. As we reflect on the life of a star, it becomes clear that its journey is intricately linked to the fate of the worlds it helps create. Each star, in its life and death, leaves an indelible mark on the universe, shaping the conditions for the emergence of planets and the possibility of life. Imagine if we could listen to the whispers of the stars as they evolve. What stories would they tell? Each supernova, each stellar wind, each pulsation of energy contributes to the ongoing narrative of cosmic evolution. The universe is a grand storybook, with stars as its storytellers, shaping the very worlds we inhabit and the intricate tapestry of existence. As we contemplate the impacts of stars on galactic evolution, we are reminded of our place in this vast cosmos. We are the inheritors of the legacy of stars, born from the remnants of their explosive deaths, and shaped by the forces they wield. In this grand cycle of creation and destruction, the stars continue to illuminate not only the voids of space, but also the profound connections that bind us to the universe. The journey of a star, from its fiery birth to its explosive demise, serves as a testament to the interconnectedness of all things. Each phase of a star's life has lasting repercussions, shaping galaxies, influencing dark matter interactions, and giving rise to new planetary systems. The cosmos unfolds in a beautiful, chaotic symphony, where stars are the instruments creating the music of existence. In this cosmic ballet, the impacts of stars resonate through time and space, reminding us of the delicate balance that sustains the universe. We are the products of this celestial evolution, forever intertwined with the stars that birthed us and the galaxies they shaped. The story of stars is not merely a tale of their existence. It is a reflection of our own journey through the cosmos, a reminder of the wonders that lie beyond our world, waiting to be discovered. As we explore the connections between stars and dark matter, we uncover the subtle yet profound ways these enigmatic forces interact. Dark matter, while elusive and invisible, is pivotal for the structure and evolution of galaxies. It forms a vast cosmic web, a framework within which galaxies coalesce and thrive. Picture this invisible matter as the scaffolding that supports the grand edifices of stars and galaxies, guiding their formation and influencing their trajectories. Within this framework, stars serve as luminous beacons, their gravitational pull weaving through the dark matter. This interaction is not merely a passive relationship. It is an intricate dance that shapes the very fabric of galaxies. The gravitational influence of stars can alter the distribution of dark matter, creating pockets where matter can accumulate and giving rise to new star formation. What does this mean for the galaxies that host these stars? The presence of stars can enhance the gravitational wells created by dark matter, leading to a more stable environment for star formation. Imagine a bustling cosmic marketplace, where the interplay between visible and invisible matter fosters a rich diversity of celestial bodies. In this context, the birth of new stars is not just a consequence of their own gravitational pull, but also a product of the dark matter's silent guidance. The distribution of dark matter also affects the orbits of stars within galaxies. Stars in the outer regions of a galaxy experience different gravitational influences compared to those nearer the center. This results in a variety of stellar orbits, creating a dynamic environment where stars can interact, collide, and merge, further enriching the galactic ecosystem. As we consider the profound influence of stellar evolution on planetary systems, we recognize that the life cycle of a star extends far beyond its own existence. The materials shed by dying stars are not merely remnants. They are the very ingredients that cultivate new worlds. When a star exhausts its nuclear fuel and transitions into the later stages of its life, it ejects vast amounts of gas and dust. This expelled material, rich in heavy elements forged in the star's core, becomes the fertile ground for the next generation of stars and planets. Imagine a cloud of gas drifting through the cosmos, laden with elements such as carbon, nitrogen, and oxygen, all essential for life as we know it. This cosmic debris, a byproduct of stellar death, can eventually coalesce under the force of gravity, forming new stars and planetary systems. The cycle of creation continues, illustrating how the remnants of one star can give rise to the next. The impact of stellar evolution on planetary systems is nuanced and multifaceted. The environment around a star during its various life stages profoundly influences the types of planets that can form. Massive stars, for example, create conditions that favor the formation of gas giants due to the intense heat and pressure they generate. In contrast, smaller stars, which burn their fuel more slowly, can foster terrestrial planets, creating a diverse array of planetary systems. As we reflect on the myriad ways in which stars shape the cosmos, we may wonder, how does this influence the potential for life? The elements produced in the hearts of stars, those necessary for biological processes, are distributed throughout the universe, creating a rich tapestry of possibilities. Each planetary system, born from the ashes of its stellar predecessors, carries the potential for life, shaped by the legacy of its stellar ancestors. The journey of a star is not isolated. It is a collective narrative woven into the broader story of the universe. Each star, through its life and death, contributes to the cosmic narrative, enriching the interstellar medium with the building blocks for new worlds. As we consider this cycle, we are reminded of the profound connections that exist between stars, galaxies, and the very fabric of life itself. The influence of stellar evolution is not just a tale of physical transformations. It is a reflection of the interconnectedness of all things in the universe. In the delicate balance between creation and destruction, stars play a pivotal role, shaping not only the galaxies they inhabit, but also the potential for life on the planets that orbit them. As we delve deeper into the cosmic landscape, we can almost hear the echoes of stars telling their stories. Each birth, each explosion, and each quiet fading into the void speaks to the intricate relationships that define our universe. The stars are not simply distant lights, they are the architects of existence, shaping the galaxies and worlds that cradle the potential for life. In this grand cosmic narrative, we find ourselves as participants in a story much larger than ourselves. The journey of the stars reminds us of our own origins and the intricate web of connections that bind us to the universe. Each star, in its luminous journey, leaves an indelible mark on the cosmic canvas, painting a picture of transformation, creation, and the eternal quest for understanding in an ever-expanding universe. Chapter 10. The Cycle Continues, Stars and Cosmic Recycling. The life cycle of stars is a majestic and intricate narrative, weaving through the fabric of the universe with profound implications. Stars are not merely luminous orbs, they are the engines of creation, their life stories echoing through the cosmos. Each phase of a star's life is a vital chapter in the grand tale of the universe, reflecting the ongoing cycle of matter, energy, and transformation. As a star reaches the end of its existence, it doesn't simply fade away. Instead, it engages in a spectacular rebirth, scattering its remnants across the cosmos. This process begins when a star exhausts its nuclear fuel, leading to its inevitable demise. Imagine the vibrant colors of a supernova explosion, a celestial fireworks display that releases a wealth of materials into space. These remnants consist of hydrogen, helium, carbon, and an array of heavier elements forged within the star's core during its lifetime. The very materials that once formed the star now become the seeds for new celestial bodies, enriching the interstellar medium. This cosmic recycling is essential for the universe's evolution. When a supernova occurs, the shock waves generated can trigger the collapse of nearby gas clouds, initiating the birth of new stars. Picture it: a cloud of gas and dust, once quiet and undisturbed, now ignited into activity, swirling and coalescing under the influence of gravity. This process of stellar birth is a continuation of a grand cycle, where death begets life, and each generation of stars contributes to the cosmic tapestry in a profound way. This ongoing cycle of star formation and destruction has been observed across various regions of our galaxy and beyond, where stellar nurseries are mingled with remnants of past explosions. The Orion Nebula, a cradle of new stars, stands in stark contrast to the remnants of supernovae scattered nearby. The contrast highlights the interconnectedness of these events, each playing a crucial role in shaping the cosmos. In this dance of creation and destruction, we find a cosmic balance that has persisted for billions of years. The implications of this cycle extend far beyond the stars themselves. Every element that composes our own planet and the life upon it originated from stars. Think of the carbon in our bodies, the oxygen we breathe, and the iron in our blood. Each of these elements was born within the cores of stars, their life cycles intertwining with ours in a beautiful and complex relationship. As Carl Sagan once remarked, we are, quite literally, a part of the universe. We are the universe made manifest, trying to figure itself out. Looking to the future, stellar evolution research continues to uncover the mysteries of how stars form, evolve, and ultimately die. Astronomers are now equipped with powerful telescopes and advanced technology that allow them to observe these processes in real time. Imagine peering into a kaleidoscope of light and color, where every flicker represents a different phase in a star's life. With each new discovery, we gain deeper insights into the mechanics of stellar nucleosynthesis and the complex interactions that govern these processes. The study of stellar evolution is also revealing how stars influence their environments. The energy released during a star's life, and particularly during supernova events, can trigger the formation of new stars and even galaxies. This interconnected web of cosmic events illustrates the delicate balance of creation and destruction that defines our universe. As we continue to explore the cosmos, we find ourselves asking, what drives the evolution of stars, and how will it shape the future of galaxies? In our quest to understand these cosmic phenomena, scientists are also delving into the role of dark matter and dark energy. These elusive components make up a significant portion of the universe, influencing the behaviors of galaxies and the formation of stars. The interplay between visible matter and these hidden forces adds another layer of complexity to the story of stellar evolution. Imagine the vastness of the universe, where the unseen shapes the seen, guiding the destiny of stars and galaxies alike. As we anticipate future breakthroughs in stellar evolution research, the potential for new discoveries remains boundless. With every advancement in technology, we inch closer to unraveling the mysteries of how stars are born, evolve, and die. The ongoing exploration of these processes not only deepens our understanding of the universe, but also fosters a sense of wonder about our place within it. Each revelation serves as a reminder of the intricate connections that bind us to the cosmos. The cycle of stars and cosmic recycling is not merely a scientific concept. It is a profound narrative that resonates with the essence of existence. Each twinkling star in the night sky is a testament to this cycle, a reminder of the life, death, and rebirth that defines the universe. As we gaze at the stars, we cannot help but feel a connection to the vastness of the cosmos, a sense of belonging to something far greater than ourselves. In this ever-evolving cosmic story, we are both observers and participants, intricately woven into the fabric of the universe. The journey of stars is our journey, their cycles reflecting the rhythms of life itself. As we continue to explore the depths of space and the mysteries of stellar evolution, we embrace the beauty of this cosmic dance, forever intertwined with the stars that illuminate our night. As we ponder the interconnected fate of stars, it's essential to appreciate the profound implications of their life cycles for the broader universe. This cosmic narrative is not merely about individual stars. It is a symphony of creation that resonates through galaxies, shaping not just celestial bodies, but the very essence of existence itself. Each star, in its brilliance and eventual demise, contributes to a grand design, a cycle that influences everything from planetary formation to the emergence of life. When we consider the rebirth of material through stellar death, we must marvel at the complexity of this process. Elements forged in the hearts of stars become the building blocks of planets and life. The death throes of a star scatter these elements across the cosmos, enriching the interstellar medium and providing the raw materials for future generations of stars. The remnants of supernovae are not just debris. They are a treasure trove of elements like nitrogen, phosphorus, and sulfur, essential for life as we know it. In this way, the explosion of a single star can lead to the birth of entire solar systems, weaving a fabric of life from the ashes of its predecessor. Imagine standing in a vast, empty space where the remnants of a supernova drift like cosmic dust. Each particle holds within it the promise of new worlds, new stars, and perhaps even new life. As these elements coalesce, they form dense regions that once again succumb to the force of gravity, igniting the cycle anew. This cosmic dance of creation and destruction is not a chaotic affair. It is a meticulously orchestrated process, governed by the laws of physics that dictate how matter behaves under extreme conditions. The ongoing cycle of star formation and destruction can be likened to a grand narrative that unfolds over billions of years. Throughout the history of the universe, stars have risen, shone brilliantly, and faded away, leaving behind observable patterns that tell a story of cosmic evolution. Galaxies like the Milky Way serve as witnesses to this tale, harboring within them the remnants of ancient stars and the vibrant gas clouds that promise future generations of stellar life. Consider the work of renowned astronomers who have devoted their lives to unraveling these cosmic mysteries. Figures like Edwin Hubble and his groundbreaking observations that unveiled the expansion of the universe, or Vera Rubin, whose studies of galaxy rotation revealed the invisible hand of dark matter. Their contributions remind us that the quest for understanding the universe is one of both science and artistry, a pursuit that transforms the abstract into the tangible. What lies ahead in our understanding of stellar evolution? The future outlook on this research is filled with promise, as advancements in technology continue to revolutionize our observations of the cosmos. Space telescopes equipped with sophisticated instruments now enable us to peer deeper into star-forming regions, unveiling details that were once obscured by dust and distance. Each new image reveals a breathtaking landscape of swirling gas and newly ignited stars, offering a glimpse into the dynamic processes at work. Moreover, the study of gravitational waves opens a new chapter in our understanding of cosmic events. These ripples in space-time, generated by the collision of massive objects, provide us with a novel means of observing the universe. Imagine the thrill of detecting the merging of neutron stars, where the energy released not only illuminates the cosmos, but also creates heavy elements like gold and platinum in the process. Each discovery enhances our appreciation for the intricate mechanisms that drive stellar evolution and cosmic recycling. As we continue to explore these phenomena, we find ourselves grappling with questions that challenge our understanding. How do different types of stars influence the evolution of galaxies? What role do supermassive black holes play in regulating star formation within their host galaxies? Each inquiry leads to new hypotheses, prompting scientists to devise innovative experiments and observations that push the boundaries of our knowledge. The cycle of star formation and destruction is a testament to the resilience and adaptability of the universe. It reminds us that even in death, there is life. Each generation of stars brings forth new possibilities, shaping the landscape of galaxies and the fabric of existence. As we gaze upon the night sky, we witness not just distant suns, but the ongoing legacy of those that came before, a reminder of the unity that binds the cosmos together. In this grand narrative, we come to understand that we are not separate from the universe, but rather an integral part of its story. The elements that compose our bodies were once forged in the hearts of stars, and in this cosmic recycling, we find a deep connection to the universe itself. The legacy of stars lives on in us, echoing through time and space in a cycle that is as beautiful as it is profound. As we look to the future, the horizon of stellar evolution research is expansive and filled with potential. With each new discovery, we embrace a deeper understanding of our place within the cosmos, an understanding that continues to inspire wonder and curiosity. The journey of stars is an invitation to explore, to question, and to marvel at the intricate web of existence that unfolds before us. Each moment spent contemplating the cosmos is a reminder of the beauty inherent in this cycle. A cycle that, like the stars themselves, continues to illuminate our path through the universe.